We can move on. This one is about the technicalities, about communication efficiency. How is federated learning different from distributed learning on a data center? For a data center, you have balanced IID data, and these data, you distribute them in a fair fashion among your machines, among your workers, and you have very good and highly optimized networks. And these machines are able to communicate with each other really fast. For federated learning, where you can think of it as federation of participating devices, you have very large number of clients, a lot of users. Your data are going to end up being unbalanced. Some users have more data, some users have less data. Your data are going to be non-IID, and you're going to have poor network connections. Sometimes a user's device is totally absent because they are in a location when there is no internet connection, and your devices are always moving. We covered this. This is just a review of federated learning. You select a subset of clients at random. Each one of them is going to get a copy of the global model, and each one of those clients that you selected is going to update their local model according to their own data. The local models are sent or communicated to the server. So you can think of it as a pull operation, some updating operation, a push operation. For if you want to use the Git type of language, this is pull, update the model locally using our own data, push it to the server, and then the server is going to do its job, aggregate, which is usually averaging to get the global model, and then you're going to repeat these steps. What are the challenges? We all know this happens to us a lot when we are uploading a file, perhaps on Google Drive. It's going to take much longer than downloading it, even using the type of internet that we have these days. Even our wired internet, the downlink is faster than uplink. Not only that, when it comes to downlink, you can take your global model, compress it using the type of compression metric that we cover in part 1 of the course. Perhaps pruning is the simplest way of doing it. And then you can reduce the bandwidth that you need to download the current model. You're downloading a compressed version of the model. When it comes to uplink, when the clients need to communicate with the server, we want to protect the data. We are not communicating the data with the server. We are communicating the model parameters, but it turns out that for some type of data and some type of models, it is actually possible to invert the model and back calculate the data that gave you those parameters or gave you those updates. We are going to see how we can prevent those types of attacks, not to reveal the identity of the data. So we need to protect those weights when we are communicating from client to the server. And there are some cryptographic protocols that you usually put around the model parameters, around those communications. And that's another reason why uplink is slower, while downlink is faster. And you want to improve the uplink, or you want to reduce the uplink communication cost. Mathematically speaking, let's put all of the weights and biases in our model. Let's simplify things. Let's say all of them is going to give you a matrix that is D1 by D2. These are the parameters of our model. T is going to index the round of training. And at time T, at round T, you are communicating the current version of your model. This is the global model on the server, to a subset of your clients, perhaps to NT of them. You pick 5, 100, 1,000 of your clients, and that's going to constitute a set of clients that are going to get a copy of your model at that iteration. Each one of them is going to do their job using their own local data. They're going to update WT to give them NT different local models per each client. So each one of you are going to have your own local model based on your local data. And then usually what is being communicated to the server is the difference between the local model and the global model. At that iteration, let's just call it HT, and each one of them depends on which client you're at. It's client dependent. And then the server is going to average these updates, takes a learning rate, and then updates the global model, which is going to get recommunicated to a random subset of the clients in the next iteration at time t plus 1. And then you keep repeating that pattern. What do we want? We want to reduce the uplink cost. We want to somehow make H cheaper to be communicated to the server. So reduce the cost of sending H to the server. There are two different paradigms. One is a structured update. The other one I'm going to explain next. What is the big picture when it comes to structured update? You restrict the updates of H to have a pre-specified structure. What do I mean? Perhaps a pre-specified structure is a low rank structure. What is that? You assume that your H, all of them, are having this structure, that it's A times B, where K is less than D1 and D2. So you're already compressing the representations of your H. K is the rank, so it's going to be a low rank. You keep K low. It's a hyperparameter that you select. There is also one other nice thing. If you want to communicate now, you need to communicate both A and B. It turns out that there is no need to communicate A. It's enough to communicate B. A could be a randomly generated matrix. And all you're doing, all you're updating on that client is B. Why is it possible? When you're communicating A, because it is randomly generated, all you need to know and communicate to the server is what random seed you used. You're a client, you're going to use a random seed, and all you need to communicate to the server is just a single number. It's just a single integer. And on the server is going to use the same random seed as the one that client I used, uses the same random number generation process, and it's going to generate a random matrix on its own. You don't need to communicate A, which is a matrix of size D1 by K. All you need to communicate is an integer when it comes to A. When it comes to B, it is the thing that your client optimized over, and B you need to communicate, which is much smaller than communicating something that is D1 by D or D1 by D2. This is K by D2. Is this clear? Okay, perfect. The other approach, which is still structured update, you randomly mask H, and your client is going to update whatever that is not masked. And this is also a predefined random mask. Again, all you need to communicate to the server is what random number generation or random seed you used. And at the same time, you need to communicate whatever that is not masked. And H is being updated locally on that machine, on that device. The other different paradigm is sketched update versus structured update. You have H, you let your device, perhaps you have enough compute on that device, you let it compute H fully. And then you're going to do some subsampling. You select a random subset of values from H. It has to be scaled because it's a random subset of your update. It's a random subset of your matrix. You need to scale it according to the probability that you use to select that random subset. And this should ring a bell. We were doing the same thing when we were doing dropouts. You would randomly mask some of your weights. And then when it comes to testing, you would use the scaled version of that weights. It's the same story here. You scale them proportionally to the random probability that you used. That's going to give you H hat, which is, it is going to end up being smaller. Only the non-zero values or non-masked values you need to communicate. And it turns out that when you do your averaging on the server, when you do this operation, because each user was masking differently and is communicating different updates, it turns out that this is actually an unbiased estimator of the true H, which is coming out of doing your summation over all of the non-masked or the true H rather than the masked version of it. This is the subsampling strategy. Another strategy is probabilistic quantization. What would you do when you want to quantize a matrix? First, let's vectorize it, which is basically flatten it so that rather than H being a matrix, it's now a vector of D1 by D2 size. You compute the maximum value of your H, the minimum value, these two quantities you need to communicate with the server, and then you're going to quantize H. How would you quantize it? These entries in that vector are either going to end up being the maximum position or the minimum position at random with some probability that is proportional to how far you are from the minimum or how far you're to the maximum position. If Hj is closer to the maximum position, then you're going to have a higher probability of choosing Hmax. So if Hj is actually your Hmax, this is probability of 1. So with probability 1, you're going to choose Hmax. Otherwise, it's going to end up being Hmin. This is 1-bit quantization. All you need to communicate is 1 bit of information and Hmax and Hmin. But this is too much of a quantization. You can do b-bit quantization. What do we mean? You divide the interval from Hmin to Hmax. You divide it equally into 2 to the power b intervals. If b is 1, you get 1-bit quantization. If b is 2, you get 2-bit quantization. And then you do the same thing. If you're closer to some number within that interval, if Hj is closer to some of those numbers, it has a higher probability of getting selected. And it should be relatively straightforward to generalize from 1-bit to 2-bit to 4-bit, etc. This strategy, b-bit quantization, works, and it's going to work beautifully if the continuous Hj, which is going to fall within this interval, is uniformly distributed in this interval. If it's all of the times closer to perhaps some zero number here between Hmin and Hmax, let's say your Hmin is -1, Hmax is +1, and Hj, the continuous version, is most of the time oscillating around 0, then 1-bit quantization is not a good quantization because your number is actually 0, but sometimes you're choosing -1 and sometimes you're choosing +1, which is not a good quantization. But if it is uniformly distributed across this interval, then that's going to end up being a good quantization. You don't lose much information. You can achieve that by multiplying this H vector by a random matrix. This is just a random rotation matrix. And because it is random, things are going to spread across this interval, and then you quantize. So these are a couple of ways for you to reduce the cost of uplink communication. You're communicating smaller stuff rather than very large H. I think it's a good time for me to stop. For those of you who have questions, I'll be around.